Hi everyone, welcome back to 3 Deviations. In today's video, we want to cover derivatives of vector functions. So in the last video, we covered limits of vector functions, so the natural next step is to cover derivatives and go through all of the calculus that we have. So why don't we just go through this very quickly. This doesn't need to be a super complicated video because the idea of it is actually very simple. So in order to take a derivative of a vector function, we only need to take the derivatives of the components such that the components are differentiable. So if I want the derivative of r of t, then I can take the derivative of f of t, the derivative of g of t, and the derivative of h of t. Now we can use the same definition of the derivative for vector functions as well, such that r prime of t is equal to the limit as h approaches 0 of r of t plus h minus r of t over h. Now we can also define a tangent vector, a unit tangent vector. So if I have my derivative vector and I want to make that a unit vector such that it would be a tangent vector, I can take capital T of t is equal to r prime of t over the magnitude of r prime of t. Now for all this, all of our differentiation rules apply. I can add them, I can sum them, I can take differences of them, I can multiply them by scalars. If I have a product, whether that be cross product of two vector functions, dot product of two vector functions, or the product of a normal function with a vector function, then I can still use the product rule. So it is Leibniz, so I can use that. So anyways, why don't we just go through a couple of examples. Here's the first example. We will find the unit tangent vector at t equals 0 for r prime of t equals 1 plus t cubed, t e to the negative t, and sine of 2t. All right, so if we take the derivative of all of this, we get r prime of t is equal to 3t squared, easy polynomial division, or differentiation. Then we got to use the product rule for the second one, such that we get e to the negative t times 1 minus t, and then 2 cosine of 2t. Fairly simple. So now we need to find our values at 0. So if we plug in 0 for r of t, we get 1, 0, 0. If we plug in 0 for r prime of t, we get 0, 1, 2. Okay, so now this is important because this allows us to determine our tangent vector. Now, our tangent vector is going to be equal to the magnitude of our vector over, our vector over the magnitude of our vector for the derivative. So if we deal with this, what we will get is we get t of 0 is equal to 1 over the square root of our components, 1 plus 2 squared, is equal to 0, 1, 2. And then we get, through multiplying all of this out, we get 0, 1 over rad 5, 2 over rad 5. So now at t equals 0, which is this point right here, we get a unit tangent vector that points up in the up in the y direction and the z direction. So we get something that looks like that as our unit tangent vector. All right. So I think that's good for this example. We were able to find the unit tangent vector fairly easily. Now we'll try another example. Parameterize the tangent line of the helix at point P. So the vector function for a helix is r of t equals 2 cosine of t, sine of t, and t. And the point we want to find it at is at 0, 1, and pi over 2. Now, in order to parameterize this, we need to determine what our t value is at this point. So we look at the point components and we look at the vector function components. So when is 2 cosine of t going to be 0? And then when is sine of t going to be 1, and then when is t going to be pi over 2? T is just going to be pi over 2 in that case, and that works out. So now we know t is equal to pi over 2. Now we need to find the derivative of our function at any point. So then we get negative 2 sine of t, cosine of t, and 1. And we find the derivative of the vector function at pi over 2, and we get negative 2, 0, 1. All right, so now what we need to do is we need to parameterize our tangent line, and we know that our tangent line is going to be pointing in the direction of the derivative of our vector function, negative 2, 0, 1. So now we plug it into our parametric equation formula that we talked about in the last unit. So we get x is equal to x naught plus at. x naught is going to be 0 from our original point. A is going to be -2, and then t is t, so we get -2t. Y equals y naught plus bt, so that's just going to be 1, because we've got 1 here, and then the 0 cancels out the bt. And then z is equal to z naught plus ct, so we get pi over 2 plus t. We can kind of see that in our graph here, so we were able to find a tangent line that is directly tangent to our helix at the point that we desire. All right, thanks for watching today's video. In the next video, we're going to talk briefly about integrals. There's not much we can do with integrals just as is, but then we translate that into arc length, and that makes things very useful for us. Thanks for watching. We'll see you in the next one. Bye.